Okay, so I'm going to talk about model-based reinforcement learning. So this, as I said, this would be a bit different lecture than previous lectures because a large part of it would be based on the research that I have done or been involved in the past few years. So this would be the part of the decision-aware model learning part of it, which I'm going to talk about what I mean by that. So far you had seen basically model-based, model-free RL. So that basically was that we have this agent that is interacting with its environment. It observes some states, reward, and then chooses some actions, and then gets a reward. And also its states goes to the next state according to some distribution P star. So I'm using P star here to basically denote the true dynamics of the environment. So P star refers to dynamics of the environment. But then, and we learned many methods, like the case that we, of course, with the case that we knew the model, it was the planning situation, that we had algorithms like value iteration, policy iteration, or linear programming. For the case that we had only access to data, RL case, we had algorithms like the different type of temporal difference learning, Q-learning included, and also methods like LSTD and then fitted Q iteration, and those type of methods. So, but here, the idea of model-based RL is that, well, as the model is, or the agent is interacting with the environment, it also learns a model of the world, maybe a simplified model of the world, and use it as kind of like internal model in order to later use it for doing some kind of maybe planning. So here the idea is that if we learn a model, for example, this I denoted by p hat, as before. So if we use a model like p hat, so we learn this model based on the data that we get from the environment, and then use this learn model, use this learn p hat and r hat in order to do some kind of internal planning or without actually interacting with the environment. So we generate this x tilde or tilde from this imagined model or hypothetical model, which is different from the true environment, and use it for the planning. And the kind of high-level motivation is that, well, doing this might have different benefits, might lead to better or more sample-efficient agents, because we are not wasting samples that has been generated before, but we are learning about the environment. Another possible benefit is that, well, maybe we are living in the same environment. The dynamics is the same, like P star is the same, but the reward is changing. So, for example, previously we had this robot, or the task that there is this robot that has to go and fetch some object from room number 1, say. And then the new task is that in the same robot, in the same environment, it has to learn how to go and fetch some object from room number 2. So probably that robot has already knowledge of how the world works, and maybe it should use or benefit that knowledge when it's solving the second task. Because the model of the environment, the structure of the rooms and everything is more or less the same. I mean, it doesn't change between 2 tasks. Only the reward function is changing. In model-free RL, we are essentially throwing out all that data that has been collected in solving the first task. And for the second task, we are starting from scratch in general. But here, we learn a model and then we reuse the model, with the only difference that the reward part is changing. So basic idea of this model-based RL is that, okay, we learn a model of the environment, this p hat, and then use the learn model for planning. So that's the kind of basic idea of model-based RL. And this has been explored in the RL community for a long time. So I think one of the earlier work has been, so for example, Sutton's work, but there have been research even before that in the control community, control theory community. Learn efficacy, there are kind of the parallels between control and reinforcement learning. Learning a model of the world in control would be similar to, would be considered as the problem of system identification. So we want to identify the system. A system means like the world here, the environment. Okay, any questions so far?
So learning a value function kind of captures implicitly some of the properties of the reward function and the transition function, I imagine, but
yes.
it's not explicit, so you can't use it planning. Is that sort of the point?
Yes, exactly. Like value function captures how the model and reward is kind of combined together to generate the return, right? And that would be expectation of it. But then they are kind of intertwined in some sense. So you can't just see the effect of models separately in the value function. That's why you can't reuse the value function for, like if you have a new task, the value function of the new task would be different from the value function of the previous task, even if the only change is the reward and not the dynamics.
Right. You would have to start over from scratch if you, yeah, okay, makes sense.
So there are things, so this is kind of like high level answer. There are ideas that maybe we can make value functions a bit more transferable. So I think that's called successor features. So yeah, basically the successor features, trying to kind of capture this idea that maybe we make reward a little bit more transferable if we assume something about the structure of the, value function more transferable if we assume something about the structure of the reward function. But in general, no. But this goal of transfer is only one reason of model-based RL, because the idea, at least, or at least the hope is that if I learn the model of the environment, I can reuse that model in order to plan, even for the same environment, and that might be more efficient compared to especially algorithms like TD, which basically process the data a little bit and then throw it out, and don't use that to learn anything about the dynamics of the environment.
Right, thank you.
Okay, so let's see how a model-based RL look like. So this is called Dyna architecture. This is the work by Reed Sutton. So this is a prototypical model-based RL algorithm. So what I'm having here is kind of like a little bit generalized form of Dyna compared to what the original paper was, but it gives you the idea. So here the basic, what happens is that, well, we have an MDP, which has P star and R star as dynamics. So we start from some state X1, and then basically we take an action as usual, where it goes to the next state X prime and R prime, and this is coming from the true dynamics. What is kind of different here is that we now update the model here too. So update the model P hat and R hat based on this observation that we move from state 1 to state 2. And then we update the value function or policy using the new sample from the real world. So for example, we use Q-learning in order to update the value function. So I think the original paper, the Dyna architecture, is usually known as work with value-based methods and use some kind of TD method for updating it, but I'm generalizing it to be able to work with policy search methods. Okay, so this part is exactly the same as the model-free aspect, but we also learn a model too. But then what happens is that we have this new loop, which is saying that for P times, like 10 times something, we draw simulated or imaginary samples from some distribution. So we say that, what if we have been in this particular states? And now take some actions according to, say, the current policy, and then receive, okay, I guess here I don't have an eraser. Yeah, so here it is just x prime coming from p hat. So we take x prime tilde from this learned model. So we generate one sample that way. And then use that sample in order to update the value function using the same algorithm as before. For example, we use Q-learning, but with this kind of hypothetical, simulated, or imaginary sample, and also the reward. So here, yeah, I guess here I had x prime, but also we need to have, so r tilde also should come from that distribution. Okay, so we have also the reward. So you see what is happening here is that the agent, after, say, every real interaction with the word, it has p interaction with its internal model. And just imagine what would happen if it does some certain action. And then try to use it to update its value function, for example, or policy. But then it goes back to the real world and then updates, take action with the kind of the new updated policy in the real world. So that's the very kind of generic architecture of model-based RL. There are variations on, say, for example, one is that, okay, is the method value-based or policy-based? And the other is, okay, so for example, other variation is when we draw, or one question is that when we draw imaginary initial samples, how should we sample that? So there are different solutions for that. Maybe one solution is just randomly choose any state in the state space, which means that, say, if I have this is the state space, I just uniformly randomly choose any state there. But then another idea is that maybe we can use, start from one of the points that we had seen before. So if in real world, so I use it maybe by green. So if we had like these real samples, for the new samples that I want to imagine, I just choose one of them randomly, and then I start the model from that point. So then I would follow a trajectory from this point or from that point. Another idea is that, well, I start from here, one of the points that I have already seen, but then add some kind of perturbation to it. So instead of exactly at that green point, maybe I start from here. Or instead of this green point, I start from a neighborhood of that. And then there are kind of more advanced methods of how to do it. Basically, kind of the idea is that maybe uniform would not be a very good idea. Maybe we want to focus on the regions of the state space that have been more difficult for the agent. If your agent had problem solving or going through like a maze in one region of the maze, then probably when it wants to imagine and improve its value function, it might be better to actually have more samples from the regions that have been more kind of difficult for the agent when it was solving while interacting with the real world. Okay, so another variation that is actually important I'm going to talk about is that how we should actually update model p hat and r hat. And I'm going to talk about it a lot. So, but yeah, so that's a basic idea of model-based R. Any question?
So to check my understanding, so basically at each step of the trajectory, first of all, you update the model of the environment, and then you randomly sample some points, and then use the current model and then update the value function policy again.
That's right, yes.
Okay, so like, okay, I see.
And I imagine that the model is actually the correct model in this, what I describe here. Just use the samples from the model and treat it as if it's a true samples.
Okay, so something like very similar to actor critic, or just, but here just we have another layer of critic, something like that, right?
I guess you can say somehow like there's a critic, but I mean, in actor critic, the critic was basically giving you how good your policy is by providing the action value function for that policy. Here, what you learn, the model is telling you what should happen if you do certain action at certain points. So it's a bit, I guess the interpretation would be a bit different from critic in actor critic, but still, this is true. That's another layer that we add in order to kind of improve the performance of.
Okay, yeah, yeah, makes sense.
Okay, so any other question? Since I mean the class is quite small, I guess it can be more interactive.
So basically, you trade off between kind of training the agent in the real world and training them in a simulation.
Yes.
Basically.
Yes. Or yes, you can see it as a trade-off, or you can actually see it as I augment it, right? Because what is really costly? Okay, so maybe not on computer simulation, like not on Atari or anything that the actual world is on a computer, but if actual world is real world, so samples are costly. It's a physical system, like I don't know, airplane is moving forward, you get sample from it. But here you add P extra samples that are just imagined to be from that. So you get P extra samples from a simulator of it, and the simulator is kind of being adapted to the real world as the agent interacts more.
Are we going to be able to talk about convergence guarantees by maybe, I don't know, placing assumptions on how much error there is in our models, or is it just not possible?
Yeah, that's a good point. The hope is that, okay, so I guess the hope is that, yes, we should be able to do that. Like if otherwise, I mean, that would not be a good thing. There are some results like convergence guarantees that would apply to this model-based RL. I'm not going to talk about that very much, but there exist some results. But I should say that compared to model-free ones, there are less theoretical work that we have about model-based RL. So model-based RL, I think, is a very kind of interesting problem because it is very promising. Sometimes in practice it works very well, and sometimes it doesn't work at all. And we don't know much about a lot of its important properties. But I mean, that all being said, there are some theoretical results that saying that this procedure is kind of working fine. Maybe just give you an idea. And for this case, like if you have a finite state and action space, what you can show is that, I mean, depends on how, of course, how you update your model. But if, so, okay, so maybe just tell me if you have a, let me see if I have a slide. Actually, I had a slide, but maybe before that. So how should I update a model? Like if you are a finite state problem, finite state action problem, how should I learn a model?
Maximum likelihood estimate.
Okay, that's good. And maximum likelihood estimate, what would be the form of maximum likelihood estimate in finite state action?
Right, so basically it will be a distribution over next state for the transition probability. And for that one, you can just count the number of appearances.
Yes. Yes, exactly. Like you can count from state, so from state X, we go to several possible X primes, right? and say you have been n times here at that state x, and 1 times in that this one, and 2 times, and then say n action times here. So essentially, your estimate of going from, say, x to one of these x primes would be, to ith one would be like this. So this would be your estimate of the probability of p of, okay, maybe I call it x.
For every action, I guess, right?
And also action, yes, for every action. So I ignore the action too. Yes, so this would be like something like that. So it would be, if I add this, so that would be like x and a. So number of state and actions that I have been, number of times I have been at state x and chosen action a, and then going to state xi. So maybe I use, I don't have it. I guess I don't have eraser here. Or maybe white is, yeah. So if I go to x prime, so that would be my estimate, right? So I can form this estimate, and what we have is that if I visit all states and actions a large number of times, this estimate converges to the true value. It would be a kind of consistent estimator. So what I get from this is p hat essentially converges to p star, which means that after all these things happening, this procedure, this planning procedure, in the beginning it might be wrong, but as I get more real interaction with the world, this becomes like closer and closer to the real model. So using generating samples from it would not have any adverse effect, at least asymptotically. In the beginning, it might be misleading, but after I have an accurate enough model here, then that would be fine. So this basically at least shows that model-based RL, I mean, if you do it correctly and you learn a good model, then the effect would not be kind of bad in some sense. You wouldn't learn something wrong. But of course, there are all sorts of conditions. I mean, it is possible that in the beginning you learn a model that encourages you to go to some certain region of the state space, and you never, because you don't have enough exploration, you never get out of that space. So you won't have any good model everywhere. So because you don't have any good model everywhere, you never go to some regions that might actually be good. So the problem is actually might be a bit complicated, but this is kind of the general idea that we can provide some theory. It has its own complications, but it is less well developed compared to model free R. Okay, so yeah, I guess I had these things: update model and then update value for according to true data and imagined data, or data from model. So this is an example of Dyne architecture when we have finite state and action space. And for the case that we use Q-learning for estimating the value function. So here you see that we are using Q-learning, or a variant of Q-learning actually. So it's kind of like, so this is actually would be expected SARSA. So it wouldn't be Q-learning, sorry. So this is expected SARSA because we have kind of expectation at the next state according to policy. So not only the action that we have selected. And then policy should be also improved somewhere. And for learning the model, we just do what we discussed on previous slide. And for the true model, well, the learned model, we do the same kind of update, Q-learning, or sorry, expected SARSA, to update the value function. So that's the idea. And kind of more generally, okay, so like I want to change maybe a bit the formulation of the algorithm. I mean, it would be the same. But here we have saying that, okay, at each loop, I'm using training sets, which is collected somehow by the environment, by interacting with the environments. And then we have these two steps, which are learning the model and learning the reward. And then we use the planner, which use this p hat and r hat in order to give us a new policy. And this planner might also use the real data too, or it might just rely on the learned model. And by planner, I mean something like value iteration, policy iteration would be one type of planner, but also you can use, say, TD type of planner like Q-learning, just that would be a sample-based planner. So this is kind of the same thing, but written a little bit differently. And then we repeat this process. Okay, so there are some issues in model-based RL, and I want to talk about them. So what are the concerns? One is that, of course, what is the choice of planner? So we have a choice of a planner here, which might be a value-based planner or a policy search type of algorithm. So we have this choice, and different algorithms of various of these types have been tried. Like the Dyna architecture, the original Dyna architecture was a value-based because it used a TD-based algorithm. But we have these algorithms like PILCO and guided policy search, which are like essentially a policy search type of methods. So we have this choice. So the other issue is that, okay, we have this planner, but how should we learn the model? And we can do model by doing some maximum likelihood estimation, like as we did in previous slides. So that was a maximum likelihood estimate. But then we can also do Bayesian model learning, essentially. We have a posterior over all possible models based on what we have already learned. And then the other thing that I'm going to talk about today is what I call decision-aware model learning. So now the issue or the question is, basically we want to learn a model that incorporates the decision problem that we want to solve into account when we learn a model. So instead of learning, like maximum likelihood model, essentially to try to learn a good predictive model of the world. And the same is true for Bayesian model learning. But maybe I shouldn't focus on all aspects of the environment. Maybe I should only focus on aspects that are somehow relevant to the decision problem that I want to solve. Or maybe focus on the learning a model which are kind of compatible with the planner that I'm going to use. So maybe a good model for a value-based type of planner would be different from a good model for a policy search type of planner. So I'm going to talk about this kind of in the second half of today's lecture, but this is another issue. So another kind of theoretical concern here is that distribution mismatch. So what happens is that if the model is not exact, which is always the case, like no model can be exact and you only have finite number of data. So there will be some differences between what your model says happens in the future to the agent versus what actually happens to the agent. So here, what I'm showing it here is using this. So the agent starts at distribution rho, and then at the next state, its distribution would be rho p star, and then rho p star to the power of 2 and to the power of 3. So this is after 2 steps, after 3 steps. So that would be the distribution of the true agent if it starts from rho. And if you recall from last lecture on Tuesday, so the value function can be written in the form of this distribution. So I think the value function, we wrote it as, say, it is essentially so if I start from x, write something. So I have kappa and then R of this thing. So there's this integration happening here, and then I have gamma to the power of k. So that's a kind of, that's a value function. I mean, there's a normalization factor here too. I guess 1 divided by y minus gamma. So you see that this is essentially the distribution of what happens in the future matters in the definition of the value function. Now, what if I have, I'm using p hat instead here in order to compute the value function. So in that case, I would have, say, same formula, but then I have p hat instead. Even if I know reward, suppose the reward is completely known. So what I learn would be some v hat of pi, which would be different if p hat and p star are different or they have some difference. And usually the thing is that as we move forward in time, like 1 step, 2 step, 3 steps, the difference between these two things increases in some measure, in some distance measure. So basically, maybe a more intuitive way of thinking about this is that prediction of what happens in the future is going to be more difficult from prediction of what happens immediately. So even if the model is accurate, relatively accurate, just predicting the next step, if I unroll it for many steps, like 10 steps, 100 steps, the prediction of where I will end up, or the agent will end up, would be different, might be different, very different from the true location or the distribution of the agent. So this is kind of another thing that complicates model-based RL, that essentially we need to, because of this kind of cumulative error of this distribution, these two distributions. And there are some work that have studied the effect of it in more theoretical ways. So I think these are that I'm kind of citing here are those papers. Okay, any question so far?
So the error will compound with a rate of O of t squared, right?
I guess that, I think that's true, yes. Okay, why do you say t squared? I guess that's true, but.
So why do I say t squared? Because in the imitation learning setting, if you have if you do behavior cloning and you have a set of expert trajectories, and even you do simple behavior cloning, it will compound as with a rate of t squared. This is mentioned by Sergey Levin in his tutorial. So yeah, I guess it's the same thing here.
Well, I guess that result is in the Dagger paper, I guess by Stefan Ross and Drew Bagnell. I think they show that in the context of imitation learning, and then they introduce a method to learn a model that is, or learn how to do imitation that would not be effective or not have that much of error. So actually, so this is kind of interesting because this paper, this last one is Andrew Bagnell, is one of the authors of that paper that I guess you're referring to. So they have these ideas how to learn a better model. And I think that's true, t squared, in this context, but I'm not 100% sure right now, top of my head. But yes, we have a behavior that is not nice, like it's not linear in terms of distribution or in terms of time step. Okay, so this is another issue that we have to think about, like how to learn a model essentially that would not be affected very much by this distribution, compounding effect, as you mentioned. Okay. Okay, so I go back to one of the first slides. So now what I'm going to focus on is the question of how we should learn a model for the task of planning. So I focus on this aspect of how this should be learned. So basically what I'm saying is that, well, how should we learn a model that is good for model-based RL? And my claim is that a conventional approach for model learning might be an overkill and may not be needed. And in difficult problems, we may not be able to do it. Okay. So any questions so far before I guess I go to the next part? Okay, so what is the conventional approach? You have already seen it. There's some example of it. Excuse me. So the idea is here is that we learn a predictive model of the environment that captures all aspects of the environment as much as possible. So that's the idea of conventional approach. And we do it through model, some maximum likelihood estimate, Bayesian inference, maximum, entropy, whatever principle that you have for learning a probabilistic model. So the point of all these methods is that they want to be a very good predictor of what happens in the future. And they are good predictors for all aspects of the environment. So if you have a multi-dimensional, say, state space, they try to learn all those dimensions equally well, more or less. But then maybe we don't actually need that. Just suppose you have an agent. So for example, you have a car, autonomous car, and you want to learn the policy for this autonomous car using a model-based RL approach, which means that, well, this is an RL agent that controls the car, but the agent learns the model of the world, how it works, and then use it for some internal planner in order to decide what action to do. So in order to find a good policy. So in this photo, what's basically I have is kind of one typical road, which has a lot of detail. Like there are all sorts of trees, there are all sorts of leaves on the trees, they are moving, and then the agent has a camera. So a model that agent should learn is that basically if I'm at the current state, so if I'm seeing this particular image, if I take then this particular action, so for example, my velocity is certain velocity, then what would be the next frame, which is going to be in like, say, 100 milliseconds in the future, for example. So what is important for this task, for the agent, is essentially to learn, say, when there is this stop sign, when to stop. Like maybe I should stop before the stop sign, and depending on my current velocity and the distance to it, the agent should predict that, okay, what the distance would be in the next time step or 10 time steps, and decide based on the dynamics of the car when is the right time to start pushing the brake. So, but if you learn a model that is basically wants to be a good predictive model of the environment, it learns everything about the environment, including the movements of the trees and the leaves on the trees, which are perhaps not relevant for this task at all. And it doesn't matter if there is a leaf on a tree that is moving in a certain way, because it doesn't change the dynamics of the car at all. But if your model is trying to predict everything that's happening on the image, so it's a kind of video prediction model essentially, or at least part of it is video prediction, then it learns those aspects too. So the point here is that not all aspects are equally relevant, but a conventional model-based approach ignores this fact and tries to learn everything. So maybe another example. So suppose you have two robots. One of them is an artist robot, the other is a cleaning robot. Suppose the robots are exactly the same physically. I mean, I couldn't find the same picture of these two robots, but suppose they are same or very similar, the same actuators, same sensors, but their tasks are different. One of them is supposed to be in a kind of a building and clean the building. The other is supposed to go in a building, maybe, or some environment, and then try to get some impression of the environment and then paint it accordingly. And suppose we somehow want to solve these problems both using model-based RL. So the dynamics of the world and how the world looks like is exactly the same. So the perception of these two robots are the same. Their actuators are the same, so the dynamics is also the same, but the tasks are very different. So a cleaning robot, for example, has to focus on like what is the topology of the building, where are the rooms, which room is connected to which one, because that's important for its, say, efficient navigation of the room. But then the artist robot should probably pay attention to maybe, I don't know, the texture on the walls or things that are related to its job of doing a painting, which are very different from the task, the things that are relevant for being an efficient cleaning robot. So if we do conventional model learning, for both of them, we learn the same model, but that might not be needed because depending on the task, these two robots should focus on two different aspects of the environment. So that's kind of why I'm claiming that conventional model approach to model-based RL might be an overkill. Any questions so far? Okay, so now I'm going to talk about how we can essentially design. So my idea is that maybe we should try to design a model learning procedure which incorporates the decision problem that we want to solve or the task that we want to solve. And the way that I'm thinking of how we can do it is that to incorporate, basically pay attention to how the model and value function or the model and policy interact with each other and design a method based on that. So we have these three components: value, policy, model. They interact with each other. I guess as kind of you mentioned, like, value and, for example, model are closely related. Like the value function would essentially be rolling out the model and just multiply things or take expectation of the reward with respect to that. So these things are related. And the same for policy. Like policy and model are closely related because, in policy gradient theorem, you had seen that the gradient of a policy is actually unrolling of the model for that discounted future reward, discounted future state distribution times something that was a function of policy, like gradient of policy, times value function, or actual value function. So actually, all three of those are kind of related, work together in order to define the policy gradients. So now I just want to pay attention to the interaction of model and the value function of policy. So this is what I call decision over model learning. And so there have been some work that I have been involved in. So this value over loss function for model learning. So it was started in 2016, and then we have this AI stats paper 2017, and then 2018 NERD paper, and we have this kind of technical report 2020. So this is by Romina, one of your TAs. Okay, so I'm going to talk about these things briefly. Maybe I can have a break, maybe for 5 minutes, and then we start. So I guess now is 12:57. Maybe start, say, 1:03. Okay, so let's start. So I'm going to talk about decision over model learning. So the question is that how to learn a model to incorporate some aspects of the decision problem or the type the planner into the model learning procedure itself. So let's try to design it, like see how it looks like, and then we get an idea of how it works. Okay, so let's try to kind of gradually formalize. Suppose that we have a true model of the environment is this P star, and then suppose this kind of orange ball is the space of all possible models that we can represent. So for example, this is a space of models that we can represent with this particular, say, neural network. any family of probabilistic model is okay. So, and I just show it with this. Here, the idea is that we have this P star, which is outside that space in general. So we can't represent it exactly. And now what we want is to learn a model here in that space that is kind of close to it. So we use it as an approximation of that P star. So what do we know about P star? We have only samples from it, because if we knew it, the problem was already solved. So we have samples in the form of xi, AI, xi prime. So xi and AI coming from some distribution, coming from samples. For example, if you have a behavior policy, this is distributed according to the data generated by this policy. And then xi primes are coming from this P star. So this would be conditioned from coming from distribution that is conditioned on xi and AI. So we have a pair of, like n pair of them. And now we want to learn a model here in some region that is kind of close to it. And we use that model to give it to a planner. And the planner gives us a policy. So now the question is that how we can do it. Okay, any ideas? Like what would be your approach if you want to solve this problem? Or maybe, I mean, this is a very vague or general question maybe. How would you, what are the important things to pay attention here?
So you could minimize some loss using the samples, like you have some parameterized function p hat,
right?
And minimize the, I guess it's empirical risk minimization in some sense.
So that's good points. Yes, we have to have some loss function and define a kind of use samples to get empirical risk or empirical loss and then minimize it. So that will be empirical risk minimization. So what kind of loss do you choose? Any idea? Or there's no single answer. So
I guess if you're predicting, I guess it depends if you're predicting probability distributions or if you're trying to predict states themselves, I guess.
Okay. Okay, so that's a good point. Like, well, but I mean, okay, so what's the real difference between predicting the state themselves or the probability of other states? Because if the environment is stochastic, we can only predict the probability of next state.
Mm-hmm.
But
I guess it seems much harder. I mean, it's what you have to do, right? Like you said, but it's harder in the sense that if the state space is very large, then just representing a probability distribution on the state space itself can be difficult, right?
That's true. That's true. I mean, that's why, I mean, learning a policy is not, learning a probability distribution, especially in high dimensional space, is not easy. So model learning part of model-based RL is not easy necessarily. But then I guess maybe you are referring to the fact that people in practice, they use just use a L2 type of loss, try to predict the next state based on L2 loss. If that's the case, then I mean that's okay if the environment is deterministic. But
yeah, or they use like a VAE or something like that.
Or yes, okay. So I guess in that case, yes. So that would be like we try to learn a probabilistic model that is somehow simpler than the true model, but we still can say something about it. So that's true. So I guess that's a good thing because basically we want to find a p hat here that is closest to p star in some sense. But then there are different choices of distances between two probability distributions. Like, should I choose D1, D2, or D3, or many others distances? So what I'm saying is that the choice of that distance function should depend on the type of planner that we are going to use. And because here what we have is that at the end of the day, we feed this p hat to this planner. So different types of planners use the model in different ways. So maybe we should respect that and design choose one of these distance functions such that it's better for the planner. So that makes it like more decision aware in some sense, so planner aware. So what kind of planners? You have seen many. Like we have seen value-based methods. In the last 2 lectures, we have seen policy search methods like policy gradients. I briefly mentioned at the TRPO, but that's the variant of policy gradient type of method. So still it's a policy search method. So let's focus on value-based ones. And for value-based ones, there are different ways, of course, to get the value function, but many of them were based on application of the Bellman operator. So they use Bellman operator in order to gradually improve their estimate or approximation of the value function. So essentially, so for example, value iteration was a repeated application of the Bellman operator, right? So yeah, I'm sure you know, but so this was the value iteration. And value iteration was implicitly a function of the model. Like P was appearing there. Previously, we were never be explicit about the P because it was always the same P here. But now we want to talk about different models, so I'm using P here. So, okay, so I have the definition here. So T star of P applied at Q and evaluated at X and A would be the same as what we had before, but here the model is essentially P. And if I change P, I get different Bellman operator. So now the first approach that I'm going to talk about is called value-aware model learning, which is basically the idea that we want to find a model that preserves the effect of the Bellman operator as much as possible. Because Bellman operator is such an important operator in finding the value functions. In many methods use it. So the goal here is just to learn a model that preserves the effect of the Bellman operator. So what does it mean? It means that, okay, if you give me a value function Q, and then I apply the Bellman operator according to P hats, the effect of it would be similar to applying the Bellman operator with respect to P star in some sense. So if I have these things, so if this was equality, so if, for example, I had equality here, then it wouldn't matter if I use P star or P hat. The effect of them from a perspective of a Bellman operator-based value-based method would be exactly the same. If they are not exact, but just approximate, then that's, of course, wouldn't be exact. But now the goal would be to make sure these two sides would be as close as possible to each other, because then the effect of them would be closer. So here the point is, what I want to do is that from this general idea, derive a loss function that says how the model should be learned. So the loss function essentially tries to make this approximation as accurate as possible. Any question?
So this basically determines what divergence we want to use between P hat and P star.
Okay. So I want to design a divergence that is good from perspective of preserving the effect of Bellman operator. Because previously, I mean, the idea was that to be a good predictive model of the environments. So for example, if we use maximum likelihood estimate, which is essentially based on the loss function, that KL divergence has the loss function. I just want, that's good for prediction, but this is going to be good for just this specific task.
Right, right. So it's not as transferable, I guess.
That's a good point. So that's a good point, and I guess it depends on how we derive it from this point on. I'm going to talk about two approaches for value-aware model learning. One of them would be more transferable in some sense, the other would be less. So one of them only works for one particular reward, dynamics and reward. The other works for larger class. But here, I guess the way I'm thinking about this is it's a kind of spectrum of how decision-aware or task-specific the model is. In one side of spectrum, we have a model that is kind of very generic. So it works for any task, doesn't care about the task. So it works for everything. And I think most of the methods nowadays are designed, or so far have been designed in this side of spectrum. Now what I want to do is that very specific. So I want to design kind of algorithms in this corner of them and something in between. So this kind of spectrum hasn't been, one side of spectrum, this side has been explored a lot. This side hasn't been explored much. And I think there is a lot of potential in between. The kind of high level intuitive argument is that we don't really need to know about everything about the environment in order to function well for most of the tasks, because the set of tasks that we solve in an environment is limited. Like the things that we do would be different, like say humans or some other animals do, would be very different from some other animal or some totally different creature. Okay, so that's the idea. Let's construct a new loss function based on this idea, that we want to make sure that T star of P hat of Q is close to T star of P star of Q. Okay, so the idea is simple. The first step at least is simple. We start from the definition of those Bellman operators applied to Q. So we have these two, and then we want them to be close. So the difference here, I guess, is only in this step that we have P star, we have P hat, we want them to be close. So let's take the difference between them and take absolute value of that as a measure of how close they are. So this basically means that I define a cost function that is defined based on P hat, P star, and value function. And when I evaluate it at state action x and a, that would be this integral of P star of a condition x and a. I compute, P star says what's the probability of going to x prime, and then I compute v of x prime there. So it would be essentially the expected value of value function at the next state. And then I compute the same thing, but according to P hat. So it would be expected value of value function according to P hat. If they're close, then these two would be similar. If they're exactly the same, they would be the same. So I can also write it as an inner product in some function space. So it would be inner product of the difference between P star and P hat times V. So this is kind of inner product is defined in this way. So, but that might be a bit more compact notation. Any questions so far on this?
So you're using V, not max Q.
Right. Okay. So that's a good point. Just I substituted this with V. And they're related.
V pi for a greedy policy would be the same, right?
V pi for the greedy policy. If it was V pi, so if it was for greedy policy, right? Yes. It's V pi. If it's a greedy policy, it would be that one. But just I define it as V to be V of x prime to be this max of Q. If you give me a Q, I take max, I get a V, which satisfies this thing. But you see later that I'm kind of not explicitly using Q, just focus on V, but doesn't really matter. I mean, you could write in both ways. Okay, so let's just talk about maximum likelihood estimate, and so that we can have a better comparison between what this objective is, this cost function, and what maximum likelihood estimate is doing. So let's talk, let's just simplify, assume that we don't want to learn a transition kernel, transition distribution, but just a distribution over state X. So some general state X. So I use P1 and P2 here. So I don't use calligraphic form of P to kind of differentiate it here. So this is just for simplification. So we have this inequality that the distance between P1 and P2 in total variation distance, or L1 distance, I mean, they're closely related if you have density, so distribution, that would be upper bounded by KL divergence between P1 and P2. So this is called Pinsker inequality. Now, what we are trying to do is that we are limited to choose P in some model space M. And then, so the goal is essentially find a P hat that minimizes the KL divergence. And we are limited to choose P in this model space. So we essentially defined the KL divergence. I expanded it in the form that X supposes countable state. So I use summation. So it would be summation of P star of X, log of P star divided by P of X, probability of X. And then I want to find a minimizer in that space. So this is the minimizer of KL divergence. But then in practice, if we don't have P star, which is the case in learning, but we only have samples from it. So we have samples in the form of Xi's, N of them, each of them coming from this P star. Then I can use the empirical measures P star N, which is essentially put a weight of 1 over N in each of those points observed. And then if I substitute it there, then I get maximum likelihood estimator, which is essentially saying that I want to find a P hat when P belongs to M, or P hat belongs to M, such that the KL divergence between this empirical measure and this P would be small. And if I substitute it and just ignoring the terms that doesn't contribute to the minimization, I would get that this is equal to finding argmax of P in some M of summation over all data of log of P of Xi. So you see that, I mean, we had in the P in the denominator here, and we had minimization, but if we substitute it, so we get minus of log of P, and then I change it to maximum, and then it would be log of this. So that would be maximizer of the likelihood, or log likelihood. So MLE essentially, probably already know it from a course in machine learning, but MLE is doing minimizing KL divergence using empirical data. Okay, so now the important point here is that the objective that we care about, which is how accurate the Bellman, the effect of Bellman operator on some value function is, according to P star versus P hat. So we have this inner product form that can be upper bounded by L1 distance between these two distributions, or total variation distance, times maximum size of maximum magnitude of that value function. So uniform norm or supremum norm of the value function. So this is basically saying that if this total variation distance is small, then what I care about is also small. But then there is another step. The other step is that, well, from previous slide, that Pinsker inequality, we know that this total variation distance is upper bounded by the square root of KL divergence between these two distributions. So if I can make KL divergence small. This makes the total variation distance small, which makes what I care about, which is the effect of the accuracy in applying the Bellman operator on value function, also small. Is this clear? And I guess this is the, okay. Yeah. But the point here, okay, so the issue here is that, okay, so next step, and then KL is, as I discussed in the previous slide, is related to a maximum likelihood estimate, which basically tries to use empirical data to minimize the KL. So if we define the model class properly and we do say, we don't overfit or underfit, then the KL the empirical minimizer of KL, which is MLE, would minimize also the KL. So if we do essentially MLE properly, we get a good bound on KL, which provides a good bound on total variation distance, which provides an upper bound on what we actually care about. But the issue here is that all these things are basically, we are saying that we are minimizing an upper bound of an upper bound. So that might be actually very loose. And this process that I described by minimizing the KL or its empirical version, MLE, it ignores any possible information about the decision problem that we have. So here on the left-hand side, this is about interaction of value function and the model. But as soon as we go to the next step, then we lose the information about it, and we just have the magnitude of the value function here. And then this also, again, lose more information. So this is, again, might be kind of overkill of why we don't need to do this if our objective is have a good Bellman operator, accurate Bellman. So any questions so far?
So how about log P times V or something like that? Is that the next step?
So have something like log P times V?
Yeah.
Okay, that's an interesting idea. No, the next step would be different. I can say that, but I don't know if this is working or not. But this is, yeah, I mean, this is kind of considered interaction of them. But how it works, I don't know. Might be. I mean, basically, you're saying that you're weighting the value function somehow in how important, or weighting the log term in log MLE according to the size of value function. So it might do it somehow, but I don't know. I don't think there is any analysis on that.
Yeah.
But that's interesting. So I guess it's worth thinking.
All right.
So now just to give you a kind of extreme example of why this might matter, suppose you just want to learn a p-hat that if you apply it to reward function, the effect would be similar to effect of p star applying to reward function. So previously, in previous slide, it was about value function, but the reward function would be a simple case, like it's a basic case. So we essentially want this to be close to each other. So which is saying that the integral of, and I'm kind of getting rid of conditioning and everything. So the simple case is that I'm saying that the integral of p hat of Rx should be close of integral of p star of R. Now suppose the p star that you have would be this distribution, kind of complicated distribution. It's not unimodal or anything that you can easily model with the Gaussian. And in some regions like this, it is actually a complex distribution or complicated distribution, which means that if you want to learn it accurately, you need to have a lot of data points. Like you need to have a lot of samples from this region, maybe less here, in order to kind of capture the distribution accurately. So something like this, you need a lot of samples, especially in, say, this region or this region, in order to learn an accurate estimate of this model according to, say, KL divergence. But then on the other hand, assume that the reward function is this one. It's a constant function. So the constant function is the reward. The model is complicated, and your goal is to find a p-hat that is close to, provide an accurate expectation of reward when we compare it with the expectation with respect to the true model. Okay, is the setup clear? So one question. So what do you think is the point of this visualization or this setup? So what kind of model do you need to learn, p-hats?
R is constant.
Yes.
So I guess it doesn't matter, basically.
Exactly, doesn't matter. Like any model that you learn, as long as it's a probability distribution, works fine. So suppose this is, like this is Gaussian, that's okay. If you use another distribution, that's okay. So it doesn't really matter what it is. In any case, as long as it's a true probability distribution, then my estimate of the reward function is accurate because it's constant. So here, but the point is that if we do MLE, it cannot benefit from this information. It tries to just learn an accurate model that is good according to KL divergence. So this is kind of the simple, I mean, it's an extreme example because in many cases, say the reward that you want to learn or the value function that you want to learn is not so simple, but it is simpler than basically, it has some structure. Okay, is this clear, this discussion? Okay, perfect. So far then, okay, we want to define a loss function. I defined a pointwise loss function or pointwise cost function. Let's take expectation over the whole state and action space and gradually make it something that we can actually use. So here, what I had before was this pointwise, so it depends on X and A. The difference between the Bellman operators are two according to P star and P hats. And then I take pointwise expectation with respect to distribution, some distribution nu over X and A, and then just take the squared value of that pointwise cost function. So that's essentially the way we define this loss function. So here there is an issue here. That the issue is that the value function is not known. We don't know the value function. So previously, I started from the point that saying that, okay, suppose this is the value function. We want the effect of Bellman operator on that value function to be close when the Bellman operator is defined with respect to p hat or with respect to p star. But if I don't know the value function, I can't do that. So there are two approaches to deal with it. So this was the first paper was about value. I call it value over model learning. So the idea was that suppose the planner uses a value function space F to represent the value function. So use say a neural network with a fixed architecture to represent your value function, suppose a DQN. So that's what your value function space would be. Or maybe you choose a linear function approximator with specific choice of basis functions. So that would be your value function space. So here we learn a model in M that is uniformly good for any function in F. So essentially we learn a model that no matter what value function we want to apply within that value function space, it would be like same goodness or same accuracy. So that's a kind of like high level idea of this original formulation of value over model learning. Then the other approach is called iterative VAL, which basically learns a model by benefiting from how approximate value iteration-based planner work, generates value functions, and use the model, and then try to learn a model that is good for this specific process. So we can say that value-aware model learning, VAM, like the original formulation, in that spectrum that I had, becomes more clear. So this is generic, this is specific. So value function space, VAM will be somewhere like here, for example. And then the other one, iter VAM, would be more specific, and maybe even closer to specific. You see how it works, and it becomes hopefully more clear. Okay, so let's talk about the first formulation. Suppose the planner uses a value function space F to represent the value function. And we want to learn a model that is good for any value function in that space. But we don't care about value functions that cannot be represented in that space. So here what we do is basically saying that we add this supremum here of our value functions in that space and consider that supremum in the definition of the loss function. So that's the basic idea. Now here, we don't need to know what V is, but we are just taking the supremum over that value function. And no matter what V it is, as long as it belongs to that value function space, this loss function essentially kind of upper bounds the difference between the true model and estimated model. Is this clear? So we have this supremum here. So, and then of course we don't have P star, but we have samples from it. So we do empirical risk minimization. We substitute samples from P star. We substitute samples that come from P star in this loss function, which we get basically a form like this, that we are learning a model, P hat of VAM, that is minimizer in some function space of the summation, the summations over the data that we have collected from the true model of supremum of V of X prime. So this is one sample from the true model X prime. And then this is expectation of, according to the model P hat. So expectation over X prime when we start from state Xi and choose action AI. So this is the idea of the loss function for VAM. And there are some more comments that I have here. One is that if we have a linear value function space, so if we can write the value function spaces in some form with some W, but we don't know the W, then this supremum can be written in a closed form. But if it's say a more complicated function space, so suppose a nonlinear neural network, then we don't have a closed form solution, which makes the optimization problem challenging, because basically I need to do minimization here and maximization here. So it's a min-max problem. And then the other thing is that we have also kind of finite sample error bound for VAM, which basically shows that how, if we have given number of samples, how accurate our model would be according to the loss function that we care about.
Sorry, a quick question. Has the community ever considered using maybe distributional robust optimization to do this kind of min-max optimization?
Distribution robust, I'm not sure. I know that.
So it's kind of like optimize the worst case performance, something like that.
So there is robust formulation over robustness over the model. Like basically we say that we don't know what the model is, but we know that it belongs to some set. So try to optimize this performance according to that set. If that's what you have in mind, then yes, that has been done in framework that is called robust MDP. So that has been done for MDP case, like for planning case, like we have algorithm like value iteration, what is robust to model. But also there are RL versions of it more recent, like past 10 years. So I guess robust MDP was like 2003 or 5, around then. But for RL, it is more recent. But that's, I guess, a more general, I think that's an interesting question, that because the model that we learn is never going to be exact or accurate, even if, so there would be some uncertainty about the model. And then the idea here is, the idea should be that the planner must consider that uncertainty in order to be robust, because otherwise it may exploit the kind of subtle differences of the model compared to the true reality. And then the performance of the policy that we learn would not be very good when we transfer it to the real world. So this is kind of somehow related to simulator to real problem, sim to real problem, but a little bit different. I mean, sim to real is, simulator is fixed, now we train on it and then transfer it. Here, simulator is adaptive because we are learning it, but still it's a simulator in some sense. But less work has been done in that area, I can say. Okay, so this is value over model learning. So there is this performance bound, it doesn't matter. What I want to kind of point out is that consider these two cases. The case that P star is actually within the model space, and the case that P star is outside the model space. So here this means that there exists a model that can exactly represent the true dynamics. Here it means that there is no model that can exactly represent it. So there would be some kind of model approximation error. So we have this thing. So the kind of these results, what I can say is that, so I consider this case as a matched case. This is this mismatched case. So in the matched case, when the model matches, the model space matches the true model, then it doesn't really matter whether you use, from model approximation perspective, it doesn't matter whether you use a VAM method or maximum likelihood estimate or minimize KL divergence. Because in both cases, you're actually can find, you get as close as possible you want to P star if you have a lot of data. But then if you have a P model mismatch, then you have to somehow project your points to this model space. So you have to project this P star to M. But then depending on how you project, you get different results. And as I kind of showed in a few slides ago, KL would be one projection, VAM would be another projection. And the result of them would not be necessarily the same. VAM explicitly try to learn something that is more relevant for the decision problem that we want to solve, like finding an accurate model value function. But MLE or KL doesn't do that. I mean, one point that I should mention is that even VAM, the way I presented it, isn't exactly going for the ultimate goal of having a high-performing agent. It is going for learning a good value function, and even not that, but learning a good Bellman operator. If Bellman operator is accurate, then the value function would be accurate too. But it is possible that we have a not very accurate Bellman operator, but still get an accurate value function. And more possibly is the case that maybe we don't have an accurate value function, but still get a good value, good policy. Just to give you an example, would be that suppose I give you, okay, so this is Q star. So we know how to get the optimal policy from it, right? So we compute the optimal policy would be the greedy policy. But now suppose I define a Q hat, which is Q star plus some constants, like 10. I shift everything constant C. The greedy policy here of this Q hat would be exactly the same as P star, even though the difference between Q hat and Q star is large. So there are these situations that value function might not be accurate, but still the policy that we get from it is a good policy. This is again a kind of extreme example, but it provides probably an intuition of why this might be the case. Okay, any question?
So I'm wondering, when we place an assumption on the value function space and say it's linear,
Right.
Using that would still give us a good model that might still work well with a nonlinear value function post hoc, right? Or is that the idea? Or
well, that might be the case, but depends. But no, the idea here is that actually we learn a model for that value function and use that value function for planning, or value function space for planning. Suppose you use a TD method using linear function approximator. If you're committed to use that value function approximator, then that model that is learned in this way would be sufficient for that purpose. But if you change the value function space, like you start from very linear function space, very simple function space, but then you make it a very complicated function space afterwards, then there is no guarantee that this model that is learned for the simple one would be useful for the complicated one.
I see, thanks.
No problem. But one thing I should say, okay, so here the formulation is, in theory, at least the loss function is, you can use it for any function space. So if you are using it with a neural network, then yes, you can, if you can solve this optimization problem, that would give you a model. And I guess one of my students are working on it to make it work with neural networks. And I think he got some good results so far, but it is kind of like preliminary stages of the research. So we don't know how well it works, but I acknowledge that this is difficult to, this might be difficult, this is difficult to solve optimally with nonlinear function approximator and everything if you have a min-max problem. But maybe in practice it works fine because, I mean, deep learning, we solve similar min-max problems, like when we deal with GANs. Even though we don't necessarily have a guarantee that we find the best solution, they perform well in practice, and maybe there would be some theory about them too at some point. But so this is the idea. If you want to do in deep RL setting or deep neural network setting, there are practical issues, there are theoretical issues that has to be done. Okay, so I skipped these results. Okay, so this is, I guess, exactly the point I was talking about a few slides ago. In the original formulation of VAML, we have this min and max, and solving this optimization problem for general arbitrary function space might be complicated. So now the idea is that maybe we try to do something a bit simpler by benefiting from how specific planner, and this is, in this case, it's approximate value iteration, generating the value function. So this is iterative VAML. So you remember, you know value iteration. So value iteration was essentially, we get QK, we apply the Bellman operator to it to get QK plus 1. So, and here we have P star. So we apply P star to VK, and VK is like max over actions. So I'm going back and forth between taking max over actions and you denoting it by V, or having Q here and having max explicitly within the Bellman operator. So this is value iteration. So let's see how value iteration works, like expand it in several steps, and then try to get a model learning from it. So suppose you start from reward function R, like you assign your Q0 by a reward function. At the next iteration, what you do is that Q1 would becomes the Bellman operator according to P star applying to V0, which would be reward plus gamma times P star of V0, which is R. And then you do it again and again, and essentially at the kth iteration, when you want to get k plus 1's value function, you have R plus gamma P star of Vk. Okay, so just let's focus on the first, maybe this step. So if I want to learn a model here that I can substitute P star with, like I can use that P hat instead of P star, what property that model should have for this first iteration? Any idea? So okay, think about like in terms of VAML, like we want a model to be good in predicting the current value function. What is the current value function here? It is V0. So if I learn a value function, and V0 is actually R here. So if I learn a value function that is close to P star, sorry, not value function, I learn a model P hat, that when I apply to reward, the effect is close to P star R, then that's all that I need. So here basically, I'm writing, for the first step, it is enough to have P hat of V0, which is R, to be equal to P star of V0. I can do this for each of these iterations. So for the next iteration, it is enough to have P hat of V1 to be close or equal to P star of V1. If it is equal, I can just substitute that P hat, and value iteration can be done exactly as before. And in general, I have it P hat of Vk should be close to P star of Vk. And we can't do it exactly, like we can have equality, but we can think about having an approximation. So this is going to be a basis of the value function model learning. So at each step of it, given at kth iteration, so for each iteration we learn a different model. So at the kth iteration, I essentially want to find a P that when applied to, say, max of Q hat Qk, what I obtained before, max over action of it, the effect would be the same between P hat and P star. So that's the kind of idea. And then if I do that, then I can use this model to define a Bellman operator and apply the Bellman operator to get the new step of the, a new estimate of the value function, which I call here by Q hat of K plus 1. And then I can substitute back this K hat and compute a new model for the next, that is good for the next iteration. So here, this is kind of iterative process. At each step, I learn a model and then use that model to improve the value function. And then the new value function is plugged in back to learn a new model. So this is for kind of theoretical perspective and analysis. In practice, probably if you want to do it, first of all, I mean, there will be some differences. One is that I also use the data that is collected instead of only relying on the learn model. So it wouldn't be purely model-based, but it could be like Dyne architecture, that some of the updates would be from model, some of the updates would be through data. So I guess that's one thing. And also, I guess in practice, probably, we don't want to solve a new optimization problem from scratch, but we use the previous solution as a warm start and continue doing it. Okay, any question? So I guess I skipped. Then, of course, we need to have a data-driven version of it. So here we have p hats, but then in practice we don't have. Sorry, we have p star, but in practice we have p data coming from p star. So we need to find the empirical version of it and solve empirical risk minimization. But that's easy, and it will be similar to the previous what we had in VAM. Here, I guess the point that maybe I should mention is that we only need to do some minimization over p. So we got rid of maximization over value functions because we are only using the most recent value function, which we know what it is, and we learn a model that is only good for it. Okay, any question?
So is it fair to say that instead of the supremum over the values, we're actually kind of iteratively improving the value alongside the model?
Yes, exactly.
Okay.
Yeah. So exactly that's the key that happens. And also this, in theory, at least if you implement this, you learn in k iteration, you learn k model instead of one single model. And each model is more specialized just to latest value function. Okay, so let's briefly talk about policy-aware model learning. So you learned about, so the idea here is that let's look at the interaction between the model and policy and try to design something for that. So I talked about policy gradient in previous lecture, but so the idea was that we have a policy parameterized by some theta, we have performance measure, which is j of rho of pi theta, and here I'm explicitly using pi to emphasize that here, this is for the case that policy grade, this performance is measured according to model P. So this is value function of policy pi theta when the model of computing that value function is coming from P, and then there's this distribution rho, which is the distribution over the initial states. And policy gradient was essentially computing the gradient of this and then update the policy to get from pi k to theta k to theta k plus 1. So here, and we had this policy gradient theorem, I mentioned it, you don't need it. So maybe the only point here is that the distribution, the future state distribution depends on the model P. And also Q also depends on model P. Because for different models, we get different Qs and we get different discounted future state distribution. So the goal of policy-aware model learning is to find a model that computes the policy gradient as accurate as possible, which means that if I use these p hats in order to compute the policy gradient, the gradient that I get would be close to the gradient that I would get if I use the true model. So essentially, we are trying to match the policy gradients and learn a model that causes that matching. And so we can show similar results that essentially policy gradient depends on how some upper bound that depends on the KL distance between two models and some other constants. So these are some constants and then the KL divergence. If we do minimization by MLE, then that's good, that's okay, because we are minimizing upper bounds. But what PAML is trying to do is to directly try to minimize the left-hand side, which is how accurate the policy gradient is according to model and according to true value. So that's a basic idea. And there is this kind of convergence results for policy gradient. I skip it. Just mention that in convergence result, the error in the model learning, according to this policy-aware model learning objective, appears. So this is kind of reassuring because it says that the error that appears in the upper bound is exactly of the same form as what we have the loss function of model learning is trying to approximate or minimize. Okay, so there are some results. So maybe maybe I have this, maybe I get a few minutes, maybe less than 10 minutes over time, but that might be interesting. So you may know something called integral probability metric, which is defined, it's a kind of concept. It's a family of distances between probability distributions, which are defined this way. Suppose we have two probability distribution mu1 and mu2 belonging to some space X. And then suppose we have a space of functions f defined on the same domain. Then the integral probability metric, IPM, is defined as this d of f of mu1 and mu2 is integral or expectation of function f according to mu1 minus expectation of it according to mu2. So this is comparing the expectation of function f according to distribution mu1 and then according to distribution mu2, and then we see how different they are. But there is a point that we choose this f to be from maximizer in some function space, that function space capital F. So we find the worst case function that we can find in that function space and compute the expectation of according to mu1 and according to mu2. So f function acts like a test function, or basically saying that how much with a function within that function space we can discriminate these two distributions. I think it's called witness function too. So it's kind of like a witness of the difference between these two. And the general idea is that if the function space f is simple, then from the perspective of that function space, two distributions might be very close or the same. And if the function space has very complicated functions, then those two distributions might be very different from that perspective. So if you go back in one of the examples that I have, that extreme example that the reward was constant. So if the function space only has one function that is constant, then all probability distributions are the same. The value of them would be the same. But if the function space is more complicated, then they would not be the same. So just, is this clear, the definition of integral probability metric?
Yep.
Perfect. So now what I'm going to do is that just give some examples of the different objectives that people have talked about and then relate all of them to integral probability metric. One is total variation. The first one is total variation distance. In that case, it would be f would be space of bounded measurable functions. So if we choose bounded measurable functions, then total variation distance would be IPM for that space. And space of bounded measurable functions is a very large space. Like you have functions that can behave very strangely. They're bounded still, but they are not smooth. They may not be continuous. That's what total variation distance try to compare to distributions with. The other is one Wasserstein distance. In that case, f would be the space of one Lipschitz function. So the functions that have some kind of nice continuity property that they don't change very much. So that would be a Wasserstein or one Wasserstein distance. And that would be a special case of VAML when f is one Lipschitz functions. But then if a VAML would be the case that f is a space of value functions. And depending on how you define a value function, that space might be small or large. Usually our value functions have a lot of structural regularities. Maybe they are smooth or some properties like that because say we use it in neural network. So this space would be perhaps smaller than one Lipschitz functions. So VAML is actually minimizing some IPM with a smaller function space. Iter VAML is choosing f to be the most recent value function. So f would be only one member, And that's the most recent value function. And then PAM, we have PAM2, which is, in this case, we again have a single function to come in that space. But then it has this form, which is expectation according to policy of log of gradient of log times q. So this is essentially contribution of a single state to the policy gradients. So that's what PAML is trying to do. But then the comparison in PAML is not between P star and P hat, but between their discounted future distribution. So that's kind of, this is kind of like IPM is kind of nice framework to see how they are different. Also, I should mention that there are some other papers that can be interpreted as doing some decision-aware model learning, but many of them were not explicit about it. Like if you go through it and see what the method is actually doing, you can see what it is. Like I guess one of them was by Joseph, Gerami, Fat, Howe, and one or two other co-authors, I can't remember. That's ICRA 2013. That's more or less explicit about it, but I guess that can be, that was, I guess, ignored in some way. And then there was Predictron, which is kind of motivated a little bit about that, but not super explicit the same way that VAML is doing. But still, there's like a few sentences mentioning the motivation that we want to have something that is task aware. I don't think they mentioned task aware. And then there's a VPN method that is not explicit, the 3QN, I'm not sure about that. And then there is this gradient aware model-based policy search, more recent work. So that is explicit about that. Mu0 is also doing the same thing. It is learning a model that is somehow decision aware or task aware. More recently, I guess, is value targeted regression. This is, again, this is actually very similar objective to ITER-VAML. And then there is this more recent at NeurIPS, there is value equivalence viewpoint that is trying to basically talk about this, something like VAML, but from equivalence class perspectives. And then outside RL, there are some papers that are decision aware, but not in RL. So I guess this is earliest is 2013. I think there is another, I guess, paper by, the closest that I could find was by Benjo, Yoshua Benjo, I think in 90s. It wasn't doing it was an RL, I think. It wasn't very explicit, but the goal was specified there. Okay, so just to summarize, the take-home message here is that, so some of you might have seen this slide. This is by Jan LeCun, who argues that reinforcement learning is the cherry on top of the cake. And what is actually important and people should focus on is unsupervised learning or predictive learning. I agree that unsupervised learning or predictive learning is very important, but I mean, one may argue that the design of the cake, the body of the cake, is designed based on what type of fruit we want to put at the top of the cake, whether it's cherry or strawberry or something else. We design the cake based on what we want to put at the top of it. So here the idea is that maybe it's important to have a predictive model about the environment in a supervised way, but it should be informed by the type of tasks or the decision problems that we want to solve. We don't need to learn about everything, be able to predict everything about the world. It is just not feasible. But we only need to learn about things that are somehow relevant for the type of tasks that the agent has to do. I think that's all. So these are some references for mostly the second part of the talk, this decision aware one. Yeah, I guess that's all. And is there any question?